Morning.
Morning.
Yeah, that hurricane last Thursday was a lot less worse than what I was expecting.
Yeah, well, they still cancelled class, so I had to.
Yeah,
I didn't have a choice. I asked. I wrote to the dean and asked because they weren't really clear about it in the message about online classes.
the last hurricane we had here was like 18,
No, 17, I think. The Irma.
17. I just know that it knocked out power in my place for a week.
Oh, that was Irma. That was 17. Yeah.
And that thing was like supposedly category 1 or 2 by the time it actually hit us.
Yeah, two. I think low two.
Yeah,
All right, we're going to get started here, folks. Sorry about having to cancel class on Thursday. Didn't really have a choice with that. We're going to probably end up not having a review day for this test. Is probably what's going to end up happening. So I'm sorry about that, but we'll just have to get through it. I wanted to remind you about the test 4 essays. It's a similar situation to what you were dealing with in test 3. There's also going to be the test 4 units quiz as well that you'll have to do. Now, the test 4 units quiz is not done on a log. You get unlimited attempts for that. So here are the notes about the essay questions. So make sure you read them carefully. If you have any questions, you can email me, but I think it's pretty clear. It's very similar setup to what you had to deal with for test 3. I would recommend doing those sooner rather than later. I think a lot of people left until the last minute with test 3, and I think it didn't do them so well because they had to do more work on that last day than they would have wanted to, I think. Okay, so let's get started here. All right, so we're going to start off with the mass defect calculations, and what you are, I'm sure you've all heard of this equation, the Einstein energy mass equation, E equals mc squared. I should move up there. There we go. And m is in kilograms, and then you've got c, which is speed of light, which is in meters per second. But that's squared, so the unit that we get for energy is kilograms meters squared per second squared, which is actually equivalent to a joule. So that's going to be the unit we're going to end up with at the end here. So the mass needs to be in kilograms, and the speed of light you'll be given. And it's a big number, speed of light. It's 2.998 times 10 to the 8th meters per second. It's pretty fast. So the idea here is that if you're given a reaction, and this would be what's known as a fusion process, because we're taking two elements and fusing them together to form something new. And you can see here we have these masses which are in atomic mass units. We generally like to use these because they're numbers that are a little bit easier to deal with than these numbers that have the exponents in them, the scientific notation. But 1 AMU is equal to this number of kilograms. You don't have to memorize this. This will all be given to you. So 1.6605 times 10 to the negative 27 kilograms. So as you can see, that's not very much. I mean, these things do not weigh very much at all. But yeah, these are atoms that we're talking about here. So the idea here is that I give you these atomic mass units, and what you'll do is you will look at the sum of the reactants and then the sum of the products. Now, the sum of the mass of the products minus the sum of the mass of the reactants will come out to be a negative value. Now, the reason for that is because we're losing mass here, going from the reactants to the products. This is why this comes out to be a negative value. The relevance of this is that this mass here can end up being converted into energy, and rather a lot of energy if we're talking about enough of these particles that are reacting here. Now, it's not easy to get this to happen. It needs a lot of energy. And this has been the holy grail for a lot of people, is to be able to create self-sustaining fusion processes where we create more energy than we use to actually make the reaction occur. But getting the control on that is the real problem here. So you can see that the calculation itself is relatively simple. We're just adding up what we're seeing here on the products and then subtracting the sum of what's on the reactants. And we come up with a negative value here. Does anybody have any questions so far? This negative value is called the mass defect. All right, so the first thing we want to do is take that value. You'll notice I leave the negative in there, but I can remove it if I want to. We're looking for the energy released, so I just can kind of drop the negative charge as we go through this, because it doesn't really matter that much. So the AMU ends up being converted into the kilograms using the conversion I have above here. And then we multiply it by the speed of light, and that's squared. And then we want this in kilojoules, so we times 1 kilojoule over 1,000 joules. Now we want kilojoules per mole. Now a mole is 6.022 times 10 to the 23 particles, and the unit on Avogadro's number is per mole. You could say, well, what per mole? Anything per mole. Numbers, particles, whatever you want. Particles per mole. But this is how we're going to get to the kilojoules per mole. You'll notice that at this point where we've got 3.08 times 10 to the negative 15 kilojoules, that would just be for one of these reacting with one of these. So one atom and one atom reacting together would give this. But if you've got a whole mole of these reacting, then we get a very large energy release, 1.86 times 10 to the 9th kilojoules. I mean, that's massive. When you consider a delta H of any chemical process, you'd be lucky to get into the hundreds of kilojoules per mole. And here you got into the billions. So this is a very highly energetic process that we're talking about here. Remembering that a mole of this would be about 2 grams and a mole of this would be about 3 grams. So, you're getting that much energy from about 5 grams of material in total. I mean, that's massive. Does anybody have any questions about that calculation? It's what you'll see on the test. I'll show you what it looks like in a bit, but there's no, I don't think it's anything incredibly difficult. Anybody have any questions? Okay. The other thing we can talk about are calculations relating to half-life, and nuclear decay is a first order process. And we've talked about first order processes before. We talked about it way back in test 1. And first order processes are characterized by the rate equation, rate equals Ka to the power of 1. And then we can talk about the integrated rate law, which we talked about as well back in test 1, and the half-life equation. You'll notice the half-life does not have any mention of A0, which is the initial amount of material that we're talking about. So that's interesting that we don't even need to know how much material we have at the beginning in order to calculate a half-life. Now, to remind you what a half-life is, the half-life is the time it takes to get to half of what we started with, right? So that's what half-life is. That's the definition of half-life. So what we can do is we can take this integrated rate law and we can rearrange it a little bit so that we can calculate this T value, which is the time. So given the half-life, we can calculate the time it takes to get down to a certain percentage of what we had before. So just showing you an example here, calculate the time required for 95.00% of a sample of plutonium-240. And I'm given the half-life here to decay. Now, why would this be important? Well, we all know about radioactive substances, and we all know radioactive substances are pretty dangerous. And the more we have of a radioactive substance, the worse it is. I mean, the more dangerous it is. But we know that radioactive substances decay, and they can decay to a point where they are no longer going to be harmful. And what's going to be important is calculating perhaps the time it takes to get to that point. So for example, if I had this plutonium-240, and I know it has a half-life of 6,580 years, that means if I start off with a gram of plutonium-240, it's going to take that long to get to half a gram, and that long again to get to quarter gram, and that long again to get to an eighth of a gram. So as you can see, each time we go through a half-life cycle, we end up with less and less of the material. But, you know, that's a cumulative amount of time that we're talking about. So we can calculate that time using a rearranged form of this integrated rate law, where we can calculate T, the time required. We can get K from the half-life using T half equals log 2 over K, natural log of 2 over K. Now, natural log of 2, if we put it in the calculator, is 0.693, so that's where that comes from. So if we have the half-life, you can see that we can calculate K. So K would equal, whoops, it's a little k, not big K. So K would equal T half, again. K would equal log 2, natural log of 2 over T half, if we rearrange that. And then we've got our T equals negative log A over A0 divided by K. Now I get this from this integrated rate law up here. You don't have to memorize this, I actually give it to you. But what's important here is this A over A0. Remember what A0 is? It's the initial amount. It's the initial amount of A. And this A here is the amount of A after time T has passed. So what that means, the upshot of all that, A over A0 is the fraction remaining after time T. Now we are given in this kind of a question a percentage. Now that percentage can be easily converted into a fraction. So 95% is going to be 0.95. Now what it's looking for here is the time required for 95.00% of a sample to decay. So what we're interested in here is not what's decayed, but what is remaining. And that's really the key word there. If 95% has decayed, then 5% is what remains. So you can see how we go ahead and do this calculation now. We calculate K using the half-life that we're given. This T half is equal to log 2, natural log of 2, which is 0.693 divided by K. So the log 2 divided by 6580 years would be 1.05 times 10 to the negative 4, and the unit there is years to the minus 1. And that's because the T half is on the bottom there, so that's per year, if you will. So that's the value of K. So using the equation we have here, T is equal to the negative log of A over A0, which is the A over A0 is the amount remaining, which is 0.0500. So we plug that in for A over A0, and that gives us the time it takes to get to 5%, which would be 28,500 years, which makes a lot of sense if you think about it, because to get to 50%, it would be 6,580 years. So you expect it to be a lot longer to get to 5%. So that's the kind of logic I want you to be considering here. Does anybody have any questions? So that's one possible way you could see the question. The other way, it says here, the sample to decay. What about if it was the sample to remain? Well, in this instance, if 95% is remaining, then that is A over A0. So we don't subtract that from 100%. We just make it 0.9500. And you can see here it'd be 489 years, which makes sense as well, because to get to 50%, it would be 6,580 years. So I'm expecting a lot less to get to 95% of what we already had. Does anybody have any questions about this equation here? Okay, we'll take a look at the practice test here, and I'll just show you those questions. Somebody's decided to make noise outside. I'm sorry about that. Okay, you can see you get these equations up here. 0.693 over K, negative 2 KT equals log A over A0. So you don't have to worry about memorizing those. We've got the periodic table here as well. Calculate the time required for a 63.60% sample to remain, or it could be remain or decay. Looks like I've got both of those examples here. Okay. Let's see. These other questions here are related to what I'm going to be talking about in a second. The mass defect question that we've already been through is this one here. And you can see it's very similar to what we had. Now, the only difference here is that you're looking for gigajoules per mole instead of kilojoules per mole. And I've given you a conversion here that allows you to convert joules into gigajoules instead of kilojoules. So 1 gigajoule is 1 times 10 to the 9th joules. So this is a good one to practice, certainly. Does anybody have any questions about the way these questions appear on the test and what you're given? Okay. So we're going to look now at modes of nuclear decay, and what we're going to find is that there are 5 modes of nuclear decay we're going to be talking about: alpha decay, beta minus decay, beta plus decay, K electron capture, and gamma decay. So let's look at the origins of this nuclear decay here. I really like this table here, and I'm just going to explain exactly what we're seeing here. So if you look at a regular periodic table, let's see, I actually do have this here, yeah. If you look at, say, everything going up to about element 20, you can see that, of course, the atomic number will represent the number of protons, and this number here, the mass number, actually represents the number of protons plus the number of neutrons. Remember, electrons don't weigh anything. But of course, the other thing we notice is that these aren't whole numbers. The reason they're not whole numbers is because there are many isotopes of each of these elements. In other words, these are elements that are going to have the same number of protons but different numbers of neutrons, and then that gets averaged for natural abundance. So I think you're all aware of that, why we don't have whole numbers on the periodic table. It also leads to every periodic table being a little bit different as well, because people have different interpretations of natural abundances of different isotopes. So you have to be careful, make sure you're using the periodic table you're supposed to be using at the time. But my point here is that if you go up to calcium 20, you can see that the mass number is 40, which indicates that the number of protons and the number of neutrons would be equal pretty much up to 20. And this is what we're looking at here in this table. See this line? You can see this line here. That's the 1-to-1 proton neutron ratio. And you'll notice that up to element 20, it pretty much goes along with that 1-to-1 ratio. But you'll notice that as we increase the number of protons in the nucleus, that the number of neutrons needed to stabilize the nucleus increases relative to the number of protons. So what I'm saying is, if you've got an element with an atomic number of 60, you don't need just 60 neutrons in order to make that stable. You would need somewhere in the realm of 90. Now, the reason for that is because remember what protons are. Protons are positively charged particles. The only thing that keeps an atom from flying apart is what's called strong nuclear forces. And in order to stabilize those strong nuclear forces and overcome that massive electrostatic repulsion that we're seeing between all of those protons, is to have more neutrons in the nucleus. So we increase the number of neutrons, so we see an increase in the number of neutrons in the nucleus to stabilize all of those protons that are in that very, very small space. So just to give you a little bit of an idea about, the size of an atom and the size of the nucleus relative to that atom, I want you to imagine a football stadium. That's going to be the total size of the atom. Then I want you to imagine a grain of rice in the middle of the field. A grain of rice right in the middle of the field. That's the nucleus. That's how much space the nucleus takes up relative to the rest of the atom. So what I'm saying there is you've got all of these protons and neutrons, as it turns out, in a very, very, very confined space. The more protons you have, the more repulsion you're going to have between them, and the more likely they are to be unstable, and the more likely it is to decay. So we can have too many protons, we can also have too many neutrons as well. That's going to lead to radioactive decay as well. Does anybody have any questions so far? Now, I will go through this in a little bit more detail later, but it turns out that elements that have too many neutrons undergo beta decay, while things that have too many protons undergo positron decay or electron capture. So we'll go through that in a bit. So let's look at how we handle this radioactive decay. It's actually not that difficult. The first one we're going to be looking at is alpha decay. And this one here, we've got uranium-238. So let's talk about what we're dealing with the notation here. So with uranium-238, this here represents the mass number of the isotope, which is, of course, the protons plus the neutrons. Because the letter here is actually a unique identifier, of the element, we don't even need to include the atomic number, but often people will put the atomic number down here. This would be 92, but this number here is optional because we already have the letter. We don't need it. But this would be the atomic number, which is, of course, the just the number of protons. So you can see here, it's relatively easy. This is 92, by the way. You can see it would be relatively easy then to calculate the number of neutrons. It would be, number of neutrons would be the mass number minus the atomic number. All right, any questions so far? All right, so alpha decay. Let's talk about alpha decay. What is alpha decay? Alpha decay is a loss of a helium nucleus. So very heavy nuclei tend to decay in this way. So what you can do if you're trying to figure out how this actually decays, you do 238U, and then I like to use this kind of notation, X, Y, and Z. And and this is what an alpha particle is. It's a helium nucleus, which is 4He. So what you can see here, it's just really algebra. So Y is equal to 234. And if I do put in the atomic numbers here, you can see that Z would equal 90. So the element that we're talking about here, we go back to the periodic table, looking for element 90, is thorium. So it would be thorium 234 would be this mystery element that we get along with the alpha particle. Does anybody have any questions so far? It's not that difficult. I don't think it's that bad. The next one is beta minus decay or loss of an electron. So things that are neutron rich or have too many neutrons tend to decay in this way. And you might wonder what I mean by that or how I can tell. I'll explain that in a bit. It's actually not that bad either, but just needs a little bit of logic. So if you've got 46 Ca, and again, we're interested in what element we're getting along with an electron. Now, an electron is given the symbol E. It doesn't weigh anything, that's why the mass number is 0. But the effective atomic number is -1 because electrons have a -1 charge. So if I put the 20 on here for the calcium from the periodic table, you can see that Z would be 21. 21 minus 1 is 20. And then the Y is just going to stay 46. And 21 is going to be SC, so it's going to be 46. SC is the element there. You've got to be a little bit careful with this -1, but that's what an electron is. Does anybody have any questions? Beta plus decay is the loss of a positron. So if we had 154 dy, and again, we're interested in this element that we're getting, and beta plus is a positron. Now, a positron is actually the antiparticle of an electron. So if you've ever watched any science fiction, you would have probably heard of antimatter. Well, that's what positron is. It's the antiparticle of an electron. And a positron has a 0 mass, just like an electron does, but the charge on it is the exact opposite charge of an electron, which is +1. So things that are proton rich tend to decay using positron emission. So 154 dy, I think it's 66 on the periodic table. So you can see that Z would be 65, Y would be 154, and 65 is the element Tb. Does anybody have any questions? An equivalent kind of decay here is K electron capture. Back in the old days, when you looked at the periodic table, in fact, it used to be that they were labeled with these letters starting at the top here, K, L, M, N, O, P, starting here at K on the first row. So when we're talking about K electron capture, it actually has an old, fairly old origin. We're looking at the absorption of an electron, which is actually in the first row of the atom's shell, first shell, and that gets absorbed into the nucleus and causes it to change into another nucleus. So when you're talking about K electron capture, the capture, it actually means the electron is not released, it's actually absorbed from the inner shell. And you can see here how that works. 190 plus the electron on the reactant side produces, here we go, going from mercury to gold. So mercury has a mass of 80 minus 1 for the electron is 79, and that's gold. So mercury is 80, gold is 79 on the periodic table. Does anybody have any questions about K electron capture? All right, the last one here is gamma decay. And gamma decay is the release of high energy photon. You'll notice that the high energy photon doesn't change the mass of the original element. All it does is it just allows the element to release some energy in the form of a high energy photon. And that's it. There's no change in mass or atomic number when we do the gamma decay. Does anybody have any questions? Okay. So let's look at, we'll look at some of those problems here that relate to this. And you can see, starting at question 3, an element has an atomic number of 80 and a mass number of 106. This element undergoes alpha decay. The atomic number of the element formed is, and then you put the answer in there. So it goes through here for alpha, then beta minus, and it asks questions about the atomic number and the mass number for each. Of course, it's different each time. So it's about the patterns. You'll see the patterns the more you do this. All right, so there you go. So that's those problems. Let's also talk about the other problems here, and it's best if I just use an example here from what you're going to see. We'll talk about this kind of problem in a minute as well. Actually, I'll do this problem now. So the other thing you can do is we can talk about nuclear equations and balancing those as well. I'm thinking that it shouldn't be too difficult for you to identify what X is in this kind of equation, but I'll just very briefly show you. So we know that the top numbers and the bottom numbers all have to add up on the same side. And I'm hoping you can see that really it just requires a bit of algebra. The only wrinkle here is just realizing that this is a neutron. There's one N here, and there's 3 of them, which means that there would be 1 plus 1 plus 1 is 3 for these. So then you can calculate the value of X, which would be the mass number of this element you're seeing down here. The neutron has a 0 charge. It's really like this, but we usually don't write the 0 because it's assumed because it's a neutron. But that's how you would calculate X there. Does anybody have any questions? All right. Let's look at questions number 14 and 15. We'll start with 14. An element has an atomic number of 45 and a mass number of 104. So determine whether it's proton or neutron rich and what the atomic number of the element would be after radioactive decay. All right, so let's see how we go about this. So I had mentioned this earlier that depending if it's got too many protons or too many neutrons, is going to determine the mode of decay that it will undergo. So neutron-rich will tend to undergo beta decay or beta minus decay, and proton-rich will tend to undergo positron decay or electron capture. So you have to be aware of whether it's neutron-rich or proton-rich. So we're going to go through and see how we can determine if something is proton-rich or neutron-rich. We'll start off with this first one here, and we've got 45 for the atomic number and 104 for the mass number. And the 45 here would be RH. So that's actually what we're dealing with. Now, stable RH would be whatever we see on the periodic table, which would be 102, 103, we'll say 103. So that would be stable RH. Now, the thing is that if we're dealing with natural abundance, then the assumption is if something is naturally abundant, then it's going to be more stable. So what I would say here is that you could calculate then what stable rhodium is here, RH, and then you could look at the number of protons in the stable, which would be 45, and the number of neutrons, which would be 103 minus 45, which is 58. For the element we're dealing with, the number of protons is still 45, but the number of neutrons is going to be 50, so 58 there, yeah, it's 59, yeah. So what you can see here is that in this first one that we're looking at, that the number of neutrons is 59, whereas when it's stable, it's 58. So what I would say is that it's neutron rich. It's got too many neutrons. Now, what I would say is if this number is less than what it would be if it was stable, then you could say it's proton rich. It would have too many protons. So neutron deficient is really an equivalent statement to saying something's proton rich, but this is neutron rich. And if it's neutron rich, what that means is it will decay by beta decay or beta minus decay, if you will. So we can use that same same notation. So it's going to be 46 and 104, and the element there for 46 would be PD. Oops, not PB, PD. There we go. So the question, remember what it was asking, first of all, we figure out that it's neutron rich in this first one. And what that means is we're looking for the atomic number of the element after radioactive decay, and the answer would be 46. It would be palladium. Does anybody have any questions? I'll do another example here. So an atomic number of 43 and a mass number of 82. So you go back up here, look at the periodic table, 43. That'd be TC. Now stable stable TC is going to be just exactly what it is on the periodic table, which is going to be 43 and 98. So the number of protons is 43, the number of neutrons is 55. So for the one that we're looking at, the number of protons is 43, which is going to be the same, but the number of neutrons is going to be 39. So what you would see there is that there's too few neutrons relative to it being stable, which makes it proton rich. So neutron deficient is the same as proton rich. Having too few neutrons is the same as having too many protons. So the proton rich elements tend to decay via positron release. And you can see that it would be 42 and 82, and 42 is MO, so 42 would be the answer. Does anybody have any questions about the proton-neutron rich questions? Okay. Okay, let's go back to where we're at here. I think we covered everything we need to cover here. All right. Well, that was actually pretty much all I had wanted to cover on Thursday, so we'll get a start here on the next part, which is concentration and colligative properties. Now, this is something that I probably, well, you know, it was added into the curriculum a bit later, you know, well after I designed this course. So what had happened was it was really supposed to be part of the first test, but I didn't want to have to rearrange every single test, so I put it at the end. Now, most of you have seen this before because you have done it in General Chemistry 1, but you may not have seen it before because I think now it's mandated that it was supposed to be moved from Chem 1 into Chem 2, so that's why I'm covering it here now. So we've got a bunch of these equations here that we're going to be talking about concentration, and in general, concentration is an amount of solute in an amount of solvent or solution. So just a bit of background here. A solute is something that gets dissolved in a solvent. And once it's dissolved, of course, we don't see it anymore. We get what's known as a solution. So those are the three terms we need to be aware of. Solute, what's being dissolved; solvent, what's doing the dissolving; and the solution, which is the end result. So we're going to look at different means of measuring concentration. And the three or four actually that we're going to look at will be percent by mass, molarity, molality, and mole fraction. So those are the four that we're going to be talking about. We're also going to be discussing two different cases of making solutions. We can have a solid being added to a solvent, and in that instance, the solution volume and the solvent volume are pretty much going to be the same. I mean, if you think about it, put in an Alka-Seltzer. Putting an Alka-Seltzer into a glass doesn't really change the volume very much. However, if we take a liquid and let me say solid solute, and here will be liquid solute, and this would be the solvent. The solution volume is equal to the solute plus the solvent volume. So that's the difference there, depending on if you're using a solid solute or a liquid solute. But you're always told if you're dealing with a solid or a liquid. The only one that really affects is molarity, because molarity is moles of solute divided by volume of solution. So that's the only one that kind of gets affected by this. So you still have to be aware of that. But I wanted you to make sure, I want to make sure you understood the distinction here between the two. The first example I'm looking at here, as you can see on the slide, says solid solutes. And this is 22 grams of phenol, which is a solid, and 160 grams of acetic acid. So the first one we're looking at is percent by weight or mass of phenol, really the same thing. If we're dealing with a percentage, it's always part divided by whole, but it's always got to do with the solute. So anything about concentration is always about the solute. So it's just the mass of the solute divided by the mass of the solute plus the mass of the solvent. So that's not too bad. We're given the masses up here. If you're concerned about which one is the solute and which one's the solvent, it's usually pretty easy to tell. For a start, generally speaking, I can tell you that solvents are always liquids. That's one thing. The other thing is there's always more solvent than solute. So whatever you're dissolving it in is always going to be more than what you're dissolving in it. So it's generally pretty easy to tell if something is a solute or a solvent. The other clue is that if you're looking for the percent by weight of something, it's always a solute. So it says percent by weight of phenol. There's a signal there that we're dealing with phenol as being a solute. All right, so everything is always with reference to the solute. So after we do this, we get 22 grams divided by 182 grams. And once we take significant figures into account, we'll come out with 12% phenol. So that would be the mass percent of that solution. Does anybody have any questions about the first one here? Now, the other thing you'll notice is that you're given a density, and the density here is going to allow you to make conversions between between volumes and masses. Now, the way that this works is we know that density equals mass divided by volume. So these are the three equations that we will be using. Well, actually, two equations we'll be using. Mass is equal to density times volume, and volume is equal to mass divided by density. So it all depends on what you need. If you need a mass, you'll use this equation here. And if you need a volume, you'll use this equation down here. Now here, looking at the formula for percent by weight or percent by mass, we had the masses already, so we didn't need to convert anything. So let's look next at molarity. Now molarity, and this is really important, molarity is moles of solute per liter of solution. So it's the entire thing here. Now this is a solid solute, so we're not really going to have to adjust for liters of solution here for this one because it's a solid solute. The first thing we want to do is calculate the number of moles of phenol. And we do that by doing 22 grams divided by 94.00 grams. So you might be wondering where that 94.00 grams come from. Well, we look up here and we see we are given the molecular formula. So we can go ahead and calculate the molar mass by adding these things up from the periodic table. Does anybody have any questions about getting the molecular weight for that? So we do have to know that molarity is moles of solute per liter of solution. The next thing here is we've got this volume of acetic acid we need. Now we are given a mass of acetic acid, which means we need a volume. So that volume is going to be mass divided by the density. Now the density here was 0.800 grams per mil. So that is D for this instance, grams per mil. 1 over D is going to be 1 mil over 0.800 grams. So it's going to be the flip of the density. So if you're looking at volume, is it mass divided by volume? It's also mass times 1 over density. We can look at it that way. So that's why I've got 160 dot grams times 1 mil over 0.800 grams times 1 liter over 1,000 mils. And this will provide us with the liters of solution here, which is 0.200 liters. So to get the molarity, it's going to be moles divided by the volume of solution. It comes out to be 1.2 M. Big M is moles per liter. So you can have it as big M or mole over L. A lot of times people will get mixed up between big M and moles. They're two different things. Moles is MOL, big M is moles per liter. Does anybody have any questions about molarity? The next one you might not have heard of is called molality. Molality, not molarity. And the definition of that is moles of solute per kilograms of solvent. Now notice it's solvent. So the amount of solution here doesn't matter. It's all about the mass in kilograms of the solvent. The significance of this is that what we notice is that a volume of a solution is actually something that can change with temperature. So one thing you'll know is that liquids tend to contract when they're cooled and expand when they're heated. So the concentration of molarity of something can change with temperature. Molality, it actually doesn't change because kilograms or mass of solvent won't change if the temperature changes. So that's why we occasionally will use molality, because it's not going to change if the temperature changes. The solvent here is the acetic acid. And what we do here is we take the mass and convert it into kilograms by using 1 kilogram over 1,000 grams. The molality is the moles of solute divided by the kilograms of solvent. We got the moles of solute up here in the previous part B, and that allows us to come up with the molality, which is 1.4 m, and little m here is equal to moles per kilogram. So those are used interchangeably as well. Does anybody have any questions about molality? Mole fraction. Now, mole fraction is a little bit similar to mass percent, except in this case, we're not looking for a percent, we're looking for a fraction. So the mole fraction of phenol here, or P, would be moles of P over moles of P plus moles of the acetic acid. The mole fraction of acetic acid would be mole of acetic acid divided by the mole of phenol plus the mole of acetic acid. So it's kind of similar to percent, except we're not multiplying by 100 here. We're just looking for a fraction. Now, in order to do that, we already have the moles of phenol. We got that from the previous part. That was up here. We got the moles of phenol. We do need the moles of acetic acid, which we can get by taking the mass and dividing by the molecular weight of acetic acid, which again, we can get from the molecular formula. So we end up getting, and the symbol we use for mole fraction is this Greek letter chi. So it looks kind of like an X. So that's chi. And you can see here, it's going to be the moles of phenol divided by the moles of phenol plus the moles of acetic acid, which we calculated up here. Now, one other way that you can get the moles from mole fraction of acetic acid is because both of these add up to 1. They always will. We could do 1 minus the mole fraction of phenol. So we don't have to actually calculate it the way I've got it down here. We can calculate it by subtracting 0.079 from 1. So if we look at the significant figures here, you can see it does work out. 1 minus 0.079. 1 is a counting number. This is 3 places past the decimal. So that would come out to be 0.921. You'll notice that there's no unit on mole fraction because the moles cancel moles divided by moles. So it's completely dimensionless. Does anybody have any questions about mole fraction? Okay. So I wanted to show you here an example of liquid solutes. And again, I'll come back to this density here and how we're dealing with that. So depending on what you need, if you need a mass, it's always going to be density times volume. And if you need a volume will always be mass divided by density, or mass times 1 over density is the same thing. So it all depends on what you want at the time. So you'll notice here, we're given a liquid here as the solute. And as I had explained earlier, this is going to make a difference to molarity, which we'll get to in a second. But here we've got mils and grams. So we've got mils of furfural, 22 mils of furfural, which means we need a mass in order to get this mass percent. In order to do that, you see the mass is going to be density times volume. So it's 22 mils times 1.13 grams per mil. That gives me grams. And then that grams can be inserted into the equation. You'll notice we are given the mass of the ethanol here, which is solvent in this case. And that's how we're getting 14% furfural, or F, here from the equation. Does anybody have any questions about this? So in the equations that you're given, or in the problems you're given, you could be given masses or volumes, depending on the kind of problem you're dealing with. That's why you've got to be prepared to use this density equation here to get what you need. Now, in this instance, for the molarity of furfural, this is distinct from the previous example. You'll notice what we have to do here is actually calculate the volume of both of these. We already know what the volume of furfural is. We're given that as 22 mils. But we also need the volume of the ethanol, and we do that by using this density equation. Mass is density times volume. And the volume is mass divided by density. I'm sorry about that. And that means we're taking the mass, which is 160 dot grams, which is what we're given in the problem, times 1 over the density, which is 1 mil per 0.789 grams. And that gives us the volume of the ethanol. The total volume, though, is going to be the sum of those two, 225 mils, which gets converted into liters. I want you to compare that to the solid solute up here. You'll notice what we did was we only considered the volume of the solvent. We didn't worry about the volume of the solute, and the reason for that is because it was solid. Phenol was a solid, so it didn't affect the volume of the solution at all. These two are liquids, which means that when you add them together, it will affect the volume, and you'll notice we had to add those together in order to get the total volume of solution. Does anybody have any questions, especially about the distinction between solid solutes and liquid solutes when we're dealing with molarity? Okay. Molality, it's not going to matter because we're only dealing with kilograms of solvent, not kilograms of solution. So we're only interested in the mass of the solvent here, which gets divided into the moles of furfural, and we end up getting the molality that way. So the only thing that gets affected by the fact that something's liquid or solid as a solute will be the molarity. Nothing else changes. Molality won't change. Does anybody have any questions? Okay, so mole fraction is the same as what we did earlier. We take the moles of what we have and divide it by the sum of the two moles. We end up getting, again, something that doesn't have any units. We can always get this mole fraction of ethanol by subtracting the furfural mole fraction from 1, just as we did previously. Does anybody have any questions? I'm hoping that for most of you, this will be review, that you've seen this before. That's why I kind of went through it somewhat quickly, because I think you should be somewhat familiar with the concentration concepts that we had talked about already. All right. Once we've got those concentrations, we can begin to talk about something else called colligative properties. Now, colligative properties are properties that are affected by the nature of particles, not by the nature of particles, but by how many particles are present, or by the concentration, if you will. And the examples include freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. So I'm going to go through examples of each of these colligative properties. So as I said, they are not affected by the nature of the particles, but simply by how many particles there are. The first one, freezing point depression. This is where, for example, we have ice, and then you've got X on top. Now, X is some sort of solute. You would have heard, if you've lived up north, then you would know that they put salt on the roads in order to help melt the ice. And this is a colligative property. If you put salt on top of ice, what will happen is the ice will melt, turn into water, so it can dissolve whatever's on top of the ice. So this is called freezing point depression. So if you have the right ratios, you can actually lower the freezing point of water to -20 degrees, which is very valuable when you're talking about sub-freezing temperatures. If you can keep water in water form below 0 degrees, then it becomes a lot less dangerous. It doesn't turn into ice. Anybody got any questions about freezing point depression? The next two, boiling point elevation and vapor pressure lowering, are somewhat related. Now, whenever you've got a liquid, there's always going to be vapor floating around above it. The definition of boiling point, or one of the definitions, is when the vapor pressure of the liquid reaches atmospheric pressure, it's boiling. In other words, when the amount of X floating around above the liquid reaches the pressure of the actual atmosphere, then it is boiling. Now, what we're doing here is if we put something in the liquid, something as solute of some sort, what's going to happen is there's going to be X's. The vapor will actually come down out of the air above the liquid and will actually try and help dissolve whatever we put into the liquid. This has two effects. It lowers the vapor pressure for one thing by just simply removing the X's above here, so vapor pressure gets lowered. And the other thing that happens is that it requires more heat or more temperature in order to turn this liquid back into X, because now you've got all this solute in here, keeping the X's kind of in the solution. So more energy is required, which means the boiling point gets elevated. So you would have seen this, an example of this as well, if ever you've cooked pasta and you've added salt to your pasta. What that does is it will raise the temperature, the boiling temperature of the water. Makes your pasta cook faster. So it's not just for taste, it will actually raise the temperature of the water as well when it boils. So that's boiling point elevation. Does anybody have any questions? The last one here is called osmotic pressure. And osmotic pressure depends upon the placement of a semi-permeable membrane in this U-shaped tube here. I know it's a little hard to see because it's not in color. But here's the idea behind osmotic pressure. A semi-permeable membrane will allow for the passage of solvent, which is water in this case, but not the passage of solute. So the solute stays on this side of the semi-permeable membrane. So what happens is water or solvent will flow past the semi-permeable membrane into the part of the tube that contains the solute. And if this is a piston, that creates a pressure. Now, an example of this, I don't know if anybody's ever done this part of a biology experiment, but what you can do is you can take a potato and you stick it in salt water. And what happens is that the potato has a skin on it, and that skin is actually a semi-permeable membrane. So what can happen is that water in the potato can leach out of the potato and into the saltwater solution, and this will have the effect of shrinking the potato. So that's an example of osmotic pressure. That is osmosis right there. There's also the possibility of what we call reverse osmosis, and reverse osmosis would be the placement of a pressure on this piston that is greater than the osmotic pressure, which can force pure solvent back past the semi-permeable membrane. That's reverse osmosis. It takes a lot of energy to do that, but that's a technique that is used to purify water, or can be used to purify water. Not entirely effective because it requires all sorts of interesting filters and things, but it can be used to do that. Does anybody have any questions about any of these colligative properties we talked about here? All right, I'm going to leave it there for today, and we'll get a start on the calculations for colligative properties on Thursday. All right, I do appreciate you coming. Thank you. And I will see you all. I'll see you all later. Don't forget to start on those test 4 essays. Thank you.
Thank you.
Thank you, Professor.
You're welcome.
Have a good day.
Thank you. Have a
You
good
too.
one.
Bye.
Bye.
Alright.